Alright, so in this video we're going to go over the basics of acids and bases, including titrations and also buffers. So the first thing you need to understand or need to remember is what a strong acid is. Strong acids and bases will ionize completely, meaning if I put it into water, I'm going to create all of the ions. So if I have hydrochloric acid and I put it into water, I am going to make Cl minus, and I'm also going to make hydronium because that hydrogen will attach and bond to the water. And I will have all of this. So if I have hydrochloric acid, I put it into water, this is what I should have in that solution. I will not have any more of this. Now, a weak acid, I should still have some of that acid molecule itself intact. So my strong acids are hydrochloric acid, sulfuric acid, nitric acid, and perchloric acid. There's a few others, hydrobromic acid, hydriodic acid. If you know what the strong acids are, you know that everything else should be a weak acid. So anything like oic acid, ethanoic acid, acetic acid, those are not strong. Group 1 and group 2 hydroxides will be strong bases. So something like sodium hydroxide or barium hydroxide. Those will create strong bases and ionize completely when you put it into water. So I would not have any more sodium hydroxide molecules intact or formula units. I wouldn't have any more of those in the solution. I should just have sodium ions and hydroxide ions. So if you know the concentration of the acid, you know the concentration of the hydronium. So if I have 1 molar solution of hydrochloric acid, I know that I have 1 molar hydronium, because when I put that into water, that's what I'm going to make. I'm going to make all the hydronium, and I should not have any HCl actually in the solution. All right, so the Ka for a strong acid will be larger than 1. So anytime that we have an equilibrium constant that is larger than 1, that means that it's very product driven. It's going to be making a lot of products. So if I dissolve something, I'm going to be dissolving all of it if the K is larger than 1. Now the pKa is very similar to the pH. pKa talks about the strength of an acid. If the pKa is small, then that means that you have a strong acid. So you need to keep this in mind. Ka will be larger than 1 for strong acids, but the pKa will actually be small. And that's because pKa is equal to the negative log of the Ka. So if I were to take a number that's larger than 1 into this formula, I'm going to get a small number. All right, so weak acids and bases will only ionize partially. So if I put it into a solution, I'm going to have some intact molecules of that acid. I'm not going to have all the hydronium that I could have made because the acid doesn't ionize completely. So in a particle diagram, I would have molecules that are still intact, acid molecules. These are the oic acids. Ammonia is a weak base. Methylamine is a weak base. Anything with the word amine in it is going to be a weak base. Now, you're not going to know the hydronium concentration of weak acids and bases unless you do an ice table. Or, if you're given the pH, you can calculate for that. So even though it's not going to produce all of the hydronium that it could produce, if you measure the pH, it still measures the concentration of hydronium. So if you have the pH, you have this. You just need to plug the pH into this equation. All right, so with a weak base or acid, the K will be much, much smaller than 1. So with the base, it's not going to be Ka, it's going to be Kb. But both of those numbers will be very, very small. They'll be less than 1. And the pKa is going to be higher because of that. All right, so BRONSTED-LOWRY conjugate acid-base pairs. Basically, if you're trying to find the conjugate of something, you're either going to add an H plus or you are going to take away an H+. So if I want to give the conjugate acid, I'm going to add H+ to it. So let's do that. For ammonia, I'm going to add an H, so it becomes NH4. But because I'm also adding a positive charge, 0 plus a 1 would give me +1. Now, if I have this one right here, well, where are you going to stick the H? You're going to stick it on the N because it's got a lone pair that actually can pull that N in, or that H in. So we're going to add it to the N, so CH3, NH3. And of course, positive because it was neutral to begin with. All right, so HCO3. All right, so if I'm going to add an H+ to it, it's going to become H2CO3. Well, that -1 charge plus a +1 will give me a charge of 0. So whenever you're asked a question, maybe can it be an acid or base? Basically, anything that has N is usually going to be a base because in most of those bases, they have lone pairs that can actually take on that hydrogen. Also, if it has a negative charge, it's likely to gain a hydrogen ion as well. All right, so let's give the conjugate base now. So for the conjugate base, you're going to take away an H+. All right, so we're going to take away an H, so we're only going to have one hydrogen, so it becomes hydroxide. And it's neutral now, so if I take away a +1, it becomes negative. Now, if I do the same thing here, I'm going to get rid of the H. And it's -1 now, so if I take away an additional positive charge, -1 minus a +1 would give me -2, so it's a -2 charge. So in order for something to be an acid, it has to have an H+ to give away. To be a base, it has to have something that can accept an H+. So it usually has to be negative, or it has to have nitrogen in it to accept that H+. All right, so pH, POH, the equations are given to you on the reference sheet. So whenever you're solving for a pH or POH, please, please, please write the formula down because otherwise you're likely to make a silly mistake. Now the pH plus the POH is equal to 14, and we know our acid-base pH scale goes from 0 to 14. Now water is kind of special because water actually will go through this reaction to a very small extent. So it'll actually make hydronium and hydroxide. Well, the constant for water is equal to 1.0 times 10 to the -14, and that's equal to the concentration of hydronium times the concentration of hydroxide. And you don't need to memorize that. That is on your reference sheet. Now, Kw, which is this number, is also equal to the Ka times the Kb, and that becomes important if you're dealing with a base and they give you the Kb. Depending on what you're doing, you may need to solve for the Ka. So remember, if you get stuck on a problem, I suggest maybe you pull out the reference sheet and see if maybe there's a formula that you can use that maybe you've forgotten about. All right, so let's look at a problem. Okay, so what's the pH of a 0.5 mole per liter of sodium hydroxide? Well, sodium hydroxide is strong. I have the concentration, so that means it ionizes completely to make all the sodium ions and all the hydroxide ions. So that means my concentration of hydroxide is equal to 0.5. This is not the hydronium concentration because that's not an acid. It's a base. Bases make hydroxide, acids will make hydronium. All right, so if I want the pH, I need the concentration of hydronium. Or I could solve for the POH and get the pH that way. So POH is equal to the negative log of the concentration of hydroxide, which is 0.5. Well, once I do that, I'm going to get 0.301. Now, if you have forgotten about this, the fact that it's a base, you might say, okay, my pH should be much higher. It should actually be higher than 7. So hopefully at that point you'll remember, oh, I solved for the POH, not the pH. All right, so the pH plus the POH is equal to 14. Well, I have the POH, so I can just plug that in there. And basically, I'm just going to subtract that from 14. So my pH will be equal to 13.7, which makes a lot more sense. So it should be a higher pH. All right, so what's the concentration of hydronium of an acid with a pH of 4? All right, so I know that my pH is equal to this. And I'm looking for my concentration of hydronium. So let's plug it into the pH equation. So 4 is the pH, is equal to the negative log of the concentration of hydronium. All right, so now let's get rid of the negative sign. So divide both sides by -1. So -4 is equal to the log of this. Well, the way to get rid of a log is the anti-log, so 10 to that power. So 10 to the -4th. I really didn't even need to do a calculation because the concentration should be simple. It should just be 1.0 times 10 to the -4th here. All right. Okay, so I have seen this question come up a few times, and it deals with the temperature. So if you increase the temperature, you actually can lower your pH. And what actually happens is when you heat something up, you're changing what K is. So you're actually changing KW. Well, when you do that, the reaction actually starts to shift more towards the product side. So this special reaction that I showed you starts happening a lot more. So it starts to go more and more and more to the product side when you heat it up because K is different now and we're making a lot more hydronium. Well, when I measure the pH, I'm measuring the pH by looking at the concentration of hydronium. Well, since that is higher, my pH will end up being lower. Now, the thing is, it's not acidic. Even though it has hydronium in it, it also has the same amount of hydroxide in it. So it's not acidic because acidic means that the hydronium concentration is more than the hydroxide concentration. All right, so now let's solve for the pH of a weak acid. Okay, so vinegar is acetic acid, essentially. It's a 0.5 molar solution. With a Ka of this, what would the pH of this solution be? What's its pKa? All right, so I have the concentration right here. Now, this is not the concentration of hydronium, though, because it's weak. It's not one of our strong acids, so that means I need to do an ice table. So if I put this into water, I'm going to make, and this is true of any weak acid, that hydrogen that's on the acid will go off and make hydronium, and then we're going to be left with this C2H3O2 with a -1. So that's my acetate ion. All right, so what's the pH of the solution? So let's do the ice table. Water doesn't get included, it's a liquid. My initial concentration of acetic acid is 0.5. Hydronium should be 0. That should be 0. Since there are 0 products, we are adding products and subtracting reactants. So at equilibrium, this should be 0.5 minus x. This should be x. This should be x. Now, it doesn't give me the pH. I'm having to solve for it, but it does give me the Ka. So I can plug this into the Ka expression. So Ka is equal to the concentration of the products divided by the reactants. And we don't include water because it's a liquid. Don't include liquids or solids. All right, so let's plug it in. Ka is 1.8 times 10 to the 5th, or negative 5th. Hydronium is X. Acetate is X. And acetic acid is 0.5 minus X. Well, Ka is very small, so I can approximate. So I can take out any X's that are being added or subtracted. So what I'm left with is X squared divided by 0.5. So when I solve for X, I'm going to get 0.003. And if you are unsure how to solve that, I would go through it on your own and make sure you get 0.003. All right, so now I've got X. Well, X is equal to the concentration of hydronium. Not the pH. I'm not done. I need the pH. So pH is equal to the negative log of the concentration of hydronium, which is this. So when I plug that in, I'm going to get 2.52. So that's my pH. And then it asks for the pKa. Well, pKa is equal to the negative log of the Ka. So that would be the negative log of 1.8 times 10 to the negative 5th. And then that would, when I plug that in, I'm going to get 4.7. All right, so in some situations you might be required to write out a reaction between an acid and a base, and there are some basic reactions that you need to know. And this will usually come into play when you have a titration problem. So if you have a strong base, or a strong with a strong, so basically a strong acid with a strong base, those reactions will produce water and some ionic compound or a salt. So your net ionic reaction will always be H plus hydroxide produces water. That's your net ionic reaction. Because anytime you put an acid, a strong acid into water, you're making H plus because it fully ionizes. Same thing with a strong base. It fully ionizes and produces hydroxide. So if I put H plus with hydroxide, I will produce water. Well, if you were titrating a strong acid with a strong base, your equivalence point should be about 7. Remember, your equivalence point is when the moles of the acid or the base added is equal to the moles of the acid or base of the thing that you started with. So when you have equal amounts of hydrogen and hydroxide, you should be at your equivalence point. Well, when we have that, when we have equal amounts of moles, I should have water at the end of that, which means my pH should be about 7. So strong acids, when they react to weak bases, will make a conjugate acid. So your basic equation is going to be H plus, because that's what comes out of a strong acid because it fully ionizes, with a weak base, and that's going to make a conjugate acid. So let's look at this reaction right here. So if I have H plus ammonia, well, the H is going to bond with this, so it's going to get an extra H, and because this is neutral, if I'm adding a +1, it becomes +1. So that's what I'm going to get if I have this reaction. Now, the thing is, I am making a conjugate acid. So at the equivalence point, when I have added the same number of the strong acid to the weak base, when I have the same number of moles, I still have an acid that's present. So the equivalence point should be below 7 because I have made an acid. So yes, the reason, if you're looking at this and you're asked where your equivalence point should lie, like what pH it should be, if you have a strong acid with a weak base, well, strong will win. Your solution at the end should be acidic, but the reason it is acidic is not because strong wins, it's because you have made a conjugate acid. So if they ask you why, It's not because strong wins, it's because you made a conjugate acid. All right, so now if you do a strong base with a weak acid, you're going to make water and a conjugate base. So this is your basic reaction here. Strong base is going to make hydroxide when it dissolves, and your weak acid, well, it reacts with that hydroxide and gives up the H plus to make water and then some conjugate base. Well, let's look at another reaction. Let's look at hydroxide plus carbonic acid. Well, the H will be removed and then will get consumed by the hydroxide to make water. And then what I'm left with, when I remove this H plus, well, I have one less H, so HCO3. And because this is neutral and I'm removing a positive one, it becomes negative. Well, if I look at this right here, this is the conjugate base. Well, at the equivalence point, should be above 7 because I have made a conjugate base. So yes, again, strong wins. Strong base with a weak acid, I should have a basic solution at the end of this titration or reaction, but it's because I'm making a base. All right, so titrations. There's some very important things for you to know about titrations and titration curves. So first of all, the end point is the point at which the indicator changes color. So you'll pick an indicator and maybe you'll start off with a clear solution and it will turn pink when you get to the end point. Well, that's the point where you stop titrating because you are right about at the equivalence point. The equivalence point is where the moles of the, in this case, I'm adding, I'm adding a base to an acid. So the equivalence point will be when I have added an equal number of moles of the base to the acid. So at the equivalence point, basically, your moles of base should equal the moles of acid that you started with. So the end point is when the indicator changes color, which is not always the same, it's rarely the same as the equivalence point, because the end point, we've actually gone just a little bit above the equivalence point. All right, so you might also be asked to choose an indicator for that titration. You're going to choose an indicator that has a pKa that's close to where the equivalence point should lie. So if you are titrating a, let's see, a strong, so in this case a strong base with a weak acid, well, strong wins, so that means my solution will be basic at the end of it. So my pH, my equivalence point, should be above 7. So I'm going to pick a pKa that's going to be close to wherever my equivalence point should end up. So I'm going to pick an indicator based on its pKa value. All right, now, so the equivalence point, remember, is the point at which the moles of acid or base that you add is equal to the moles of whatever it was present. So remember, you're titrating something, you're adding remember, you have your burette, and then you're going to be adding it to a titrant right here. So whenever you're adding this, eventually you get to the point where you have the endpoint, so the indicator changes color, and that indicates that you have hit the equivalence point, which is when the moles of the acid added is equal to the moles of base present, or vice versa. Okay, so it's not the same as the endpoint, because usually the endpoint is slightly above the equivalence point. Now, if you know what the equivalence point is, you can get the molarity of that acid or base. So whatever it is that you're titrating, you can figure out what the molarity is based on how much of the other thing you added. All right, so the buffer region, that's another important region of the titration curve. So the buffer region, if you remember, a buffer is a weak acid with its conjugate base, or a weak base with its conjugate acid. So as you're adding your acid or your base, you're making a conjugate of whatever that is. Well, when you get to about here, about halfway to the equivalence point, the amount of your conjugate acid with your weak base, or vice versa, will be equal. So at this point, when we are slowly changing the pH, it's not very gradual, it's going up just a little bit, just a little bit. This point is the buffering region. And the reason it's not changing is because we actually have a buffer there. We have a weak acid with its conjugate base. So a buffer prevents dramatic changes in pH. So your buffering region will happen right here, where your pH is changing, but only slightly. And right here, this halfway point to the equivalence point, so here's my equivalence point, halfway region right here, the pH that I have is actually going to be equal to the pKa. So that's important for you to remember too. So the equivalence point is when the moles of the acid added is equal to the moles of the base present, or vice versa. The halfway equivalence point is when the pH is equal to the pKa. If you know that, you know what the pH is at that point, you can actually determine what the Ka or the Kb of the acid or base is. So at this halfway equivalence point, I have a buffering region. So my concentration of my weak acid is equal to the concentration of my conjugate base, and then my pH is going to be equal to my pKa. Okay, so if you're asked to draw a titration curve, you need to make sure you pay attention to where the equivalence point should be, where the pH should start and end. So if you're starting off with an acid and you're adding a base to it, your pH should be below 7. If it's a strong acid, it should be closer to 0. If it's a weak acid, though, it can be about 2 or 3. And then when you're going up to your ending point, think about where you're going to end up. So if you're titrating a strong base with it, it's going to be above 7, maybe not quite at 14 though. And think about where your equivalence point should lie. Should it be above 7, below 7, at 7? Think about those things when you draw your titration curve. Also think about maybe you're starting off with a base and adding an acid. So if you're starting off with a base, you're going to start off with a higher pH. If it's a strong base, it should be closer to 14. A weaker base, maybe about 12. Okay, so if you're asked for a pH of a neutralization reaction, basically if you're asked for a pH during a titration or after a titration, you're going to use a BCA table. Now if you're just asked for molarity, you can use stoichiometry. So you know the reaction. So maybe it's strong acid with a strong base. You can use stoichiometry to figure out what your molarity was, because at your equivalence point, the moles of whatever you're adding is equal to the moles of whatever you had present. Or you can use this equation. This molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base, provided it's just a 1-to-1 ratio. Okay, now something else to keep in mind is when you have a polyprotic acid, like phosphoric acid, because we have more than one H, every time that you have a polyprotic acid, only one hydrogen comes off at a time. So if I were to have a titration curve of a polyprotic acid, I'm going to see multiple equivalence points. So right there, that first equivalence point, that's when I pull off the first H. Then when I get to the second one, that's when I pulled off the second H. So I have multiple parts of that graph. So every time I have an equivalence point, I've pulled off another H. All right, so a buffer, remember, is a weak acid with its conjugate base or a weak base with its conjugate acid. So it's important to remember if you read a question and you see that you have a weak acid with its conjugate base, or vice versa, you have a buffer. So buffers resist changes in pH, and that's because you have both components there. So you would have an acid and also a base. So let's say that I have acetic acid. And I don't know, just in this scenario right here. If I have acetic acid, well, its conjugate acid or conjugate base would be acetate. So this is my weak acid, my conjugate base. So if I have both of those present, what can happen is, let's say that I add an acid to it. Well, if I add an acid to it, this is going to react to it and neutralize the acid. Well, if I add a base to it, I also have an acid present, and that will react to the base that I'm adding, and that will neutralize it. So I have two components here, so basically it will resist changes in pH because one or the other thing is going to react to whatever I'm adding to it. All right, so anytime that you see that you have a buffer, if it's asking for the pH, use your Henderson-Hasselbalch equation. And this makes it very, very simple to solve for pH. So you're going to take the pKa and then add that to the log of the concentration of your base divided by the concentration of your acid. Now, if you have the same concentrations here, so let's say it's, I don't know, 0.5 and 0.5, well, that should be 1. Anytime I take the log of 1, I get 0. So the pH will be equal to the pKa, provided that these concentrations are the same. And that's really the best way to build an acid, is to pick something that has a pKa close to the pH that you want to keep your solution at, and then keep these concentrations equal. All right, so if we're building a buffer, the pH of the buffer is determined by the pKa. So you're going to look at your weak acids. You're going to pick one that has a pKa that's close to the pH that you want. So if you want a pH of 8, you're going to find something with a pKa of about 8. And then what you're going to do is you're going to have equal concentrations of your weak acid and your conjugate base. And that's basically what you need to do if you're building a buffer. You're going to pick an acid with a pKa close to the pH that you want, and then keep your concentrations equal. All right, so remember, if we have a titration curve, this region right here where the pH is just slowly changing here, that's called our buffering region. And this is our equivalence point. So the equivalence point is when your moles of whatever you've added is equal to moles of whatever you had present. This point is called my halfway equivalence point, and that is going to be when my conjugate acid is equal to my weak base, or vice versa. And at that point, my pH is going to be equal to my pKa. With buffer capacity, basically, if you have more of your components, so more conjugate acid and weak base, you're going to have more of a capacity. So that means basically you can add more acid or base to it without changing the pH. All right, so when we're looking at this problem right here, it says that we have 50 milliliters of acetic acid is titrated to the halfway equivalence point with 25 mils of sodium hydroxide. So which of the following options shows the correct ranking of the molarities? So I'm not even going to bother doing any kind of math with this. I'm just going to think about it really quick. Because if I know that I'm at the halfway equivalence point, I know a few things actually. I know that my weak acid concentration should be equal to my conjugate base. So I know those concentrations should be equal at the halfway equivalence point. Well, I also know something else about the halfway equivalence point. I know that the pH is equal to the pKa at the halfway equivalence point. So I know that the pH at this point must be 4.7. So that means that I have an acidic solution, which means that the concentration of my hydronium is greater than the concentration of my hydroxide. So based on that, well, my weak acid should be equal to this, and this one it is. And also, I know that it is an acidic solution, so it should have more hydrogen ions than hydroxide. So it should be choice B based on that. And that was without me doing any kind of math at all. Basically, all I did was use the fact that I know at the halfway equivalence point, the weak acid is equal to the concentration of the conjugate base, and that the pH is equal to the pKa. Now, one of the things that they could do on the test is they could ask you to compare acid strength. So there's a few ways that you could actually do that. The first is with the pKa. So if you have pKa values, the larger the pKa, the weaker the acid. So here we have two pKa values. The higher one will be the weaker acid. So anytime that you have a higher pKa, that means that it's a weaker acid. So this is the weaker one, which means that there will be less hydrogen ions in that solution. So this one should have more hydrogen ions in the solution. So if we were actually looking at two solutions that start off with the same concentration, so if you have 1 mole per liter of this acid, 1 mole per liter of this acid will actually have a lower pH than this one because it is a stronger acid. So that means I'm going to have more hydronium when I measure the pH. So if you increase the number of oxygens, that will increase the acid strength. So let's look at two acids and see which one is stronger. If we have this one versus this one, well, they're pretty much the same except for the number of oxygens. So the one with more oxygens will give us a stronger acid, which will lead to more hydrogen ions being in the solution. Another thing you could do is if you do not have a binary acid, so this does not count for acids with only two elements in it, if you add more electronegative acid or atoms in that structure, that's going to create a stronger acid. So if we're looking at these two acids, they're very similar in structure except for one has chlorine and one has iodine. Well, if you remember, electronegativity increases going up and to the right. If you look it up on the periodic table, chlorine will have a higher electronegativity value than iodine. So that means this will lead to a stronger acid. So this acid will be stronger. Okay, so if you add more CH groups, then the acid is weaker. So let's look at an example. We've got two acids here. We've got ethanoic acid, which has two carbons. And this one has 3 carbons. It has all of these CH groups added to it. So if you have more of those CH groups, that actually leads to a weaker acid. So this acid will be weaker than this one. So this should actually be the stronger acid. Now, there's another way to compare acid strength, and that is only with a binary acid. So that means that you only have 2 elements. So that means you have hydrogen and then some other element. So acid strength will increase going down the group and to the right of the periodic table. So as I go down this group right here, hydrobromic acid will be stronger than hydrochloric acid, which will be stronger than hydrofluoric acid. If I'm going to the right, if I'm comparing water to hydrofluoric acid, well, hydrofluoric acid will be a stronger acid than water.